Hello, Math 1224. This is Dr. P with Lesson Launch 404, Integration, Egyptian Style. And yes, I am referring to the ancient Egyptians. Now, you're probably wondering how that's possible because calculus was invented long after the ancient Egyptians were around. But here's a little bit of mathematics history for you. You may or may not know that the Egyptians did actually have a mathematical object in their vocabulary that was like fractions, which is pretty remarkable for a civilization as ancient as the Egyptians were. So they had symbols to represent fractions like these, which are called unit fractions. They're called unit fractions because in each case, the numerator of the fraction is 1. But what they didn't have, at least according to my honestly pretty shaky understanding of the history, they didn't have symbols for fractions like 2/3 that are not unit fractions, that have numbers other than 1 in the numerator. But one thing that they would do is they would represent quantities like 2/3 by representing them as sums of unit fractions like 1/3 and 1/3, and also 1/2 plus 1/6. And sometimes in the math history parlance, these are called Egyptian fractions. It's like an Egyptian fraction decomposition of 2/3. So what does all this have to do with calculus? Well, we're going to show in this video that there are some integrals that we can make easier by decomposing a rational function, that is a polynomial over a polynomial, into simpler fractions that can be added together. So let's take, for example, the integral of x dx over x squared minus 4x minus 5. Now remember, anytime you see an integral, you should always start by asking yourself, is there anything easy that I can do that might make this integral easier to calculate? For example, you might try a substitution, you might try parts, you might try looking in a table. And actually, this integral, I think, can be handled by looking in the table that we talked about in the last 3 videos. But I'm going to illustrate another technique. Now first, let's just check and make sure that a u substitution won't work. If I set u equal to the denominator of this rational function, x squared minus 4x minus 5, then my du is going to be 2x minus 4, which isn't so close to what I have here. I have an x here, and there's just no constant I can multiply x by to get 2x minus 4, so I don't think this is going to work. Makes me sad. Okay, so we're going to try something other than that. That's not going to work so well for us. So instead, we're going to try using the following idea. We know that x over x squared minus 4x minus 5, that's equivalent to x over x minus 5 times x plus 1. So I'm going to start by factoring the polynomial in the denominator. And here's the big idea, which I have to be honest, if I hadn't been taught this idea, I don't know how I would have ever come up with the idea. This is one where it's so clever, it's hard to come up with it if nobody's ever told you. But we could write this fraction as a sum of some number, some constant a, over x minus 5, plus some constant b over x plus 1. And this is called the method of partial fractions. So we're going to try and figure out if we can write this rational function as a sum of some constant over x minus 5 plus some constant over x plus 1 by choosing the right constants a and b. So the question is, what are the right choices of a and b? And now this, what we have in front of us now, is actually an algebra problem. It's not really a calculus problem. We'll have a calculus problem once we're done with the algebra. But first we have the algebra problem of figuring out what constants a and b will make this sentence true, this sentence, for all values of x. And that's actually really crucial. We want this to be true for all values of x. All right, so I'm going to zoom out a bit, just put that over here, and then we're going to try and figure out what the appropriate values of a and b are. Okay, so we want x over x minus 5, x plus 1, to always be equal to a over x minus 5 plus b over x plus 1. Now, if I multiply both sides by the product of these two binomials here, I will get that x equals a times x plus 1 plus b times x minus 5. Okay, that's by multiplying both sides by that polynomial there. The reason that we get a times x plus 1 is because multiplying by this cancels this factor of x minus 5, or that denominator, gives me a times the other factor. And similarly here, this cancels the denominator of x plus 1, leaves a factor of x minus 5. Okay, now remember, we want this statement to be true as a statement about polynomial functions. In other words, we want these to be exactly the same polynomial function. So in other words, we want x to be equal to ax plus a plus bx minus 5b. So we want x to be equal to a plus b times x, so I'm just gathering up these linear terms here, plus a minus 5b. We want these to be exactly the same function of x. All right? So what this means is that if these are going to be exactly the same function of x here, then that means that this needs to be 1, so that that term matches this term, and this needs to be 0. Okay? So I'm going to solve the system of equations a plus b equals 1 and a minus 5b equals 0. Now, depending on what you've been up to, it may have been a while since you've solved a system of equations, but my favorite approach here, I think, is to go ahead and multiply this one by 5 and try and eliminate one of these variables. So 5a plus 5b equals 5, and then a minus 5b equals 0. And then adding those two equations together gives me 6a equals 5. So that tells me that a is going to need to be 5/6. And then returning to this equation here, I think will tell me that b needs to be 1/6. That's what remains to make 1. So I think it is true. So I'm going to zoom out again here. So I think I can say that x over x minus 5, x plus 1, is always equal to 5/6 over x minus 5 plus 1/6 over x plus 1. And if I were to take this side of the equation, get a common denominator, and add those terms together, I believe I would get exactly this. You could actually verify that for yourself. All right. Now, why in the world would I want to do that? You're probably wondering at this point why we've gone to all this trouble just to write a nice rational function, totally innocent, minding its own business, this rational function here, as a sum of two other rational functions. Well, the answer is, very simply, this is way easier to integrate. That's way easier to integrate. So let's see if we can do that. So if I integrate x dx over x minus 5, x plus 1, that's the same as the integral of 5/6, put that in brackets, over x minus 5, plus 1/6 over x plus 1 dx, because these this function and this function are exactly the same. They're equivalent. So let's see if I have any luck integrating the function on the right. Now, because that's a sum of two different functions on the inside, I can split that up and treat this as two separate integrals here. And I'm going to pull the constants out while I'm at it. 5/6 times the integral of dx over x minus 5 plus 1/6 integral of dx over x plus 1. And then that's going to be equal to 5/6 times natural log of the absolute value of x minus 5. Remember, that's one of our basic integration rules there. Plus 1/6 natural log absolute x plus 1. Need a little bit more room here. Plus c. And there we have it. So I think I have an antiderivative of the original function. And we got it by treating this as though it's one of those Egyptian fractions we didn't know how to write, and writing it as a sum of two somewhat more basic things. Now, at this point, you may be wondering, well, gosh, how do I know that that's actually the right antiderivative? Well, one answer to that always is you can try taking the derivative and seeing if you get back something equivalent to this. Now, the first thing that's going to happen is you're going to get this, and then you probably have to algebraically rework that and see if that turns into this, which it should. But there is one other thing we can do, and that is we can pull back our integration table, and because I think that there's a rule for dealing with functions like this in the integration table, and just see if we come up with exactly the same thing, or if we come up with something different. Now at this point I'm looking at the integration table on a different device, so I don't have to bother with pulling it in here, but you might want to look at the integration table yourself and see if you can find an entry in the table that tells us how to deal with a function like this. In fact, you might want to pause the video and see if you can track it down. It's not quite obvious when you look at the table. There is one that works, but it doesn't quite look the same as this. You have to be a little bit flexible in your reading of the table. But there is a rule. That rule is number 27 that says the integral of cx plus d over x minus a, x minus b, dx, that's equal to, and now I'm going to have to zoom out a bit. My writing is too big on this thing still. But that's going to be equal to, according to the table, that's equal to 1 over a minus b times ac plus d. That's barely readable. There we go, that's better. ac plus d, natural log x minus a minus bc plus d times natural log of absolute x minus b, all of that plus c. God, that's gross looking. I mean, interpreting this rule is probably a little bit less work than finding the appropriate partial fractions, but only by a little bit, I think. Anyway, let's see if we can make this original integral here conform to this rule. I believe we can. So in this case, I believe that c is going to be the coefficient of x in the numerator, that's 1, and then that d is going to be 0 because there's no constant term here, just the x by itself. And then that denominator gives us a equals 5, b equals -1. So I think that if we interpret Rule 27 correctly, we get 1 over a minus b is 6. I'll go and just write that out. And then ac plus d, well, ac plus d, that's going to be, I believe that's 5. Natural log of x minus a, that's x minus 5. And then bc plus d, well, b times c, that's -1, plus d, that's -1, times natural log of x minus -1, that's the same as x plus 1, plus c. And if we work that out, we get 1/6, 5, natural log of x minus 5. Terrible penmanship there. Plus natural log of x plus 1 plus c. And if you look at this, look at this result and our earlier result, I think you'll recognize those are exactly the same thing. Only difference is, in the upper one, I've distributed that factor of 1/6. So there you have it. The table and the method of partial fractions agree. Partial fractions is a bit more work and a bit more trouble, but it is a method which, if you learn to use it, you can use it to integrate many, many, many functions where you have a polynomial over polynomial. Not all of them, not absolutely all of them, but many of them, and certainly at least the ones where the denominator factors completely into distinct linear factors. So anyway, that's the end of this video, and I will see you in class.